What if the answer to life's origins isn't confined to Earth? What if life didn't begin here at all? Instead, could it have been seeded from the farthest reaches of space, carried on cosmic dust or comets, traveling across the vastness of the universe? This is the core concept behind the Panspermia Hypothesis, a fascinating and provocative theory suggesting that life on Earth may have originated from elsewhere in the cosmos. Imagine, for a moment, that we might not be as unique as we think. What if the building blocks of life are widespread across the universe, carried through space by natural forces? This idea pushes the boundaries of traditional science, challenging our understanding of biology, chemistry, and the very nature of life itself. The Panspermia Hypothesis proposes that life, or at least its building blocks, could have originated beyond Earth and been transported to our planet, perhaps in the form of microscopic organisms or organic compounds, carried on comets, meteorites, or even space dust. This theory, though highly speculative, has captivated the imaginations of scientists, philosophers, and enthusiasts for decades. The idea that life on Earth could be a cosmic accident, or perhaps even a cosmic inevitability, offers a profound perspective on our place in the universe. In this video, we'll dive deep into the Panspermia Hypothesis, exploring its history, the science behind it, and the compelling evidence that either supports or challenges this theory. From ancient ideas to modern scientific investigations, we'll unravel the mystery surrounding one of the most intriguing ideas in the search for life beyond our planet. The birth of the Panspermia Hypothesis, ancient ideas and early thought. The idea of panspermia is not a modern invention. In fact, its roots can be traced back to ancient civilizations. The concept of life's cosmic origins was first proposed by Greek philosophers in the 5th century BCE. Anaximander, one of the pre-Socratic philosophers, suggested that life on Earth might have originated from other worlds and that living organisms could travel through space, entering the Earth's atmosphere. This early thought paved the way for what would later be known as panspermia, though it remained largely speculative for centuries. In the 19th century, as the field of microbiology began to flourish, scientists started to consider the possibility that life might not have originated solely on Earth. One of the most significant proponents of panspermia during this period was the Swedish chemist and philosopher Svante Arrhenius. In 1903, Arrhenius published a paper in which he suggested that microscopic life forms, such as bacteria, could be carried through space by radiation pressure, the force exerted by sunlight. He proposed that these microscopic organisms could survive the harsh conditions of space, traveling through the cosmos and potentially seeding life on distant planets, including Earth. Arrhenius' theory was based on the assumption that microorganisms could remain dormant for extended periods while being transported through space. He argued that these microorganisms, upon reaching a suitable environment, could reactivate and begin the process of evolution. This early scientific argument laid the foundation for modern-day panspermia theories, blending ancient ideas with the emerging understanding of biology and physics. In the following decades, the idea of panspermia gained traction, although it remained largely speculative. The discovery of microorganisms that could survive extreme conditions, such as those found in deep-sea vents or within ice crystals in the polar regions, hinted that life might be more adaptable and resilient than previously thought. This growing body of evidence suggested that life might not be confined to Earth but could potentially exist elsewhere in the universe or even travel between celestial bodies. Modern-day research and the search for evidence. Fast forward to the present day, and the Panspermia Hypothesis has gained renewed interest, driven by advancements in space exploration and astrobiology. In the last few decades, scientists have made significant progress in understanding the conditions that might allow life to survive the harsh environment of space. Research into extremophiles, organisms that thrive in extreme conditions on Earth, has provided key insights into how life might survive the journey across the cosmos. One of the most promising lines of evidence for panspermia comes from the study of meteorites. Some meteorites contain organic molecules, specifically amino acids, that are the building blocks of life. In 1950, scientists discovered that meteorites such as the Murchison meteorite, which fell in Australia, contained amino acids that are commonly found in living organisms. These organic compounds could have formed in space, suggesting that the building blocks of life might exist beyond Earth. However, while these compounds are necessary for life, they are not proof of life itself. The debate continues as to whether these molecules are the result of natural processes in space or whether they are the remnants of ancient life forms. Another important aspect of modern panspermia research is the study of the harsh conditions in space. Can microorganisms truly survive the vacuum of space, exposure to intense radiation, and the extreme temperatures found in the cosmos? Some studies suggest that certain extremophiles, such as the bacterium Deinococcus radiodurans, can survive in space for extended periods. In 2007, scientists conducted an experiment in which they sent Deinococcus radiodurans aboard the European Space Agency's Photon M3 spacecraft. The bacterium was exposed to the harsh conditions of low Earth orbit for over a year. Upon returning to Earth, some of the bacteria were still viable, demonstrating that life can endure the extreme conditions of space for significant periods. Additionally, the discovery of water on other celestial bodies, such as Mars, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, has bolstered the idea that life could exist, or could have existed, elsewhere in the solar system. These moons contain vast oceans beneath their icy surfaces, offering potentially habitable environments for life. If life exists or has existed on these moons, it might have been seeded from Earth or another distant planet, making panspermia a plausible explanation for the origins of life in our solar system. Challenges to the panspermia hypothesis, the case for Earth-based origins. While the panspermia hypothesis is intriguing, it is not without its critics. The theory faces several challenges that make it difficult to prove. One of the main criticisms is the issue of contamination. If life were to have originated elsewhere and traveled to Earth, how would we distinguish between life that came from another planet and life that evolved here on Earth? The possibility of contamination by Earth-based microorganisms complicates the search for extraterrestrial life. Another challenge to panspermia is the survival of life during its journey through space. Space is an extremely hostile environment. Even if microorganisms could survive the vacuum of space and radiation, the high-speed impacts with planetary atmospheres or surfaces could destroy them. Some scientists argue that the conditions of space travel are so extreme that it is highly unlikely for life to survive the journey. Additionally, the panspermia hypothesis does not address the ultimate question of how life began in the first place. If life was seeded from elsewhere, it only shifts the question of its origin to another location in the universe. The true origin of life remains a mystery, and panspermia does not offer a definitive answer. The implications for the search for life beyond Earth. As we continue exploring the panspermia hypothesis, it's essential to understand the broader implications this theory holds for the search for life beyond Earth. If panspermia is indeed a valid explanation for the origins of life on our planet, it could radically reshape our approach to astrobiology, the study of life in the universe. One of the most exciting possibilities raised by the panspermia theory is the idea that life is not unique to Earth. Rather, life could be widespread across the universe, carried across vast distances by comets, asteroids, and dust particles. This perspective challenges the assumption that life must develop independently on each habitable planet. Instead, it opens up the possibility that life could be interconnected throughout the cosmos, with common origins in distant regions of space. Astrobiologists have long sought definitive evidence of life beyond Earth, particularly in our solar system. Mars, with its history of liquid water and relatively hospitable conditions in the distant past, has been a focal point in this search. If panspermia is true, then it's conceivable that life, perhaps in a microbial form, might have once existed on Mars, or could still exist there in some dormant state. The idea that life could have migrated from Mars to Earth or vice versa further complicates the search for extraterrestrial life, as it suggests that the boundaries between planets are not as distinct as once thought. The moons of Jupiter and Saturn also present intriguing possibilities for panspermia. Europa, for instance, is thought to have a subsurface ocean beneath its icy crust. Scientists believe that this ocean could harbor life, protected from the harsh conditions of space by the thick ice shell above it. If life exists there, it could share a common origin with life on Earth, potentially carried across space by an ancient comet or asteroid impact. Similarly, Enceladus, another icy moon, has been found to eject plumes of water vapor, which might contain organic molecules. These moons are not only prime targets in the search for life, but they also support the idea that life could have spread across the solar system. The possibility of life elsewhere in the universe raises profound questions about the nature of existence and our place in the cosmos. If life exists on distant exoplanets, could it have been seeded from a dying star or a distant supernova? Could intelligent civilizations be out there, looking up at their skies and wondering if we, too, are a product of cosmic seeding? These questions inspire scientists to continue their search for exoplanets in the habitable zone, where conditions might be right for life to thrive. Discoveries like the identification of Earth-like planets in other star systems further fuel this curiosity, suggesting that the conditions for life may not be unique to our planet. The role of space exploration in testing the panspermia hypothesis. In recent years, space exploration has provided us with an unprecedented ability to investigate the Panspermia Hypothesis. Missions to Mars, the exploration of icy moons like Europa and Enceladus, and the study of meteorites have all contributed to our understanding of the potential for life beyond Earth. However, while these missions are invaluable, they have also revealed the complex nature of life's survival in space and the difficulties inherent in proving panspermia. The discovery of organic molecules in meteorites, as mentioned earlier, is one of the most significant pieces of evidence supporting the idea that life's building blocks could be widespread in space. However, organic molecules themselves are not proof of life. They are simply the raw materials that could eventually lead to the formation of life under the right conditions. The search for signs of life on Mars, for instance, has not yet yielded conclusive results, though several missions have found compelling evidence that the planet once had liquid water, which is crucial for life as we know it. If panspermia is correct, it raises the possibility that Mars could have once hosted life, or that life from Earth might have influenced the evolution of any potential Martian organisms. One of the most intriguing findings comes from the study of space dust. Tiny particles of dust that travel through space might carry microorganisms or organic compounds that could survive the journey through space. In 2014, researchers from the European Space Agency, ESA, suggested that space dust could be an important vehicle for transferring life between planets. In their study, they found that certain bacteria could survive the extreme conditions of space for extended periods, potentially enduring the journey from one celestial body to another. If this finding is accurate, it could provide a crucial piece of evidence for the panspermia hypothesis, as it suggests that life could be transferred between planets via cosmic dust. The debate: could life have originated independently on Earth? While panspermia presents an exciting possibility, it is far from the only explanation for the origin of life on Earth. The prevailing theory among scientists is that life originated on Earth through a process known as abiogenesis, the gradual evolution of life from non-living chemical compounds under the right conditions. According to this theory, the early Earth had a combination of water, heat, and chemical precursors, which led to the formation of the first simple organic molecules, eventually leading to the creation of life. Abiogenesis remains the most widely accepted theory, but it, too, faces significant challenges. The exact processes by which life arose from non-living matter are still not fully understood. Some scientists argue that life's origin is so complex that it might have required a series of highly improbable events to occur. Others believe that the conditions on early Earth might have been more favorable to the formation of life than we realize, and that abiogenesis is not as improbable as it seems. Future research directions and the search for proof. One of the most exciting developments is the continued exploration of Mars. NASA's Perseverance rover and other missions are studying the Martian surface in detail, searching for signs of past life and the conditions that might have once supported life. The presence of organic molecules on Mars, along with evidence of ancient rivers and lakes, points to a history of habitable conditions. If panspermia is correct, then Mars might have played a role in the spread of life to Earth, or vice versa. Future missions to collect Martian soil samples and return them to Earth for analysis could provide critical clues about the planet's past, and possibly reveal evidence of life that was transported from Earth to Mars. Similarly, the exploration of the icy moons of Jupiter and Saturn offers intriguing possibilities. Missions like NASA's Europa Clipper, set to launch in the next few years, will study Europa in greater detail, focusing on its potential for harboring life beneath its icy crust. If life does exist on Europa or other moons like Enceladus, and if it shares a common origin with Earth, it would provide strong evidence for the panspermia theory. Understanding how life could survive in such extreme environments, protected by layers of ice and subjected to intense radiation, could also offer insights into the resilience of life itself. On Earth, advances in laboratory experiments are also shedding light on the origins of life. Scientists are conducting experiments that simulate early Earth conditions to understand how life might have formed from non-living chemicals. Some researchers are even attempting to recreate the building blocks of life in laboratory settings, testing whether these molecules could spontaneously form under the right conditions. If life can emerge from these experiments in the laboratory, it would lend further support to abiogenesis, the idea that life could arise naturally on a planet like Earth. This research doesn't necessarily contradict the panspermia hypothesis, but it does suggest that life could have emerged independently on Earth. The broader implications for humanity. As we look to the future, the panspermia hypothesis, whether proven or disproven, invites us to reflect on the broader implications for humanity. If life is indeed widespread throughout the cosmos, it could reshape our understanding of life's rarity and significance. It suggests that life might be a natural consequence of the universe's chemical processes, scattered across the stars and potentially waiting to be discovered. Alternatively, if life originated on Earth and evolved through abiogenesis, it underscores the uniqueness of our planet and the delicate conditions that allowed life to emerge. Understanding how life began on Earth can help us protect the environment and the precious ecosystem that sustains us. It also highlights the fragility of life in the universe and the need to protect our planet as we explore other worlds. Regardless of the outcome, the search for the origins of life is not just about finding answers, it's about asking the right questions. It's about pushing the boundaries of human knowledge and venturing into the unknown. The Panspermia Hypothesis encourages us to look beyond our planet and think about the possibility of life beyond Earth, sparking curiosity and wonder that have driven scientific exploration for centuries. In the end, the Panspermia Hypothesis is more than just a scientific theory, it's a gateway to profound philosophical questions about life, the universe, and our place within it. It reminds us that, in the grand scheme of things, we are all part of a vast cosmic web, and the story of life on Earth may just be one chapter in a much larger tale, written across the stars. Conclusion. The Panspermia Hypothesis, though still unproven, opens a door to limitless possibilities in our quest to understand the origins of life. As our exploration of the cosmos continues, we may one day find the answers to the questions that have fascinated humanity for centuries. Until then, we must keep searching, keep questioning, and keep imagining the infinite ways in which life may exist beyond the confines of our home planet. Could life on Earth be the result of cosmic seeding? Or is it a product of the unique conditions found here, on our blue planet? Only time and further research will reveal the truth. And so, we leave you with this question: is Earth truly the cradle of life, or just one stop in a grander cosmic journey of life spreading across the stars?